So I was supposed to give a talk about diversity of terrestrial planet climate states, and this talk's supposed to be accessible to everyone. So if you're an expert in the field, might be some review stuff, but hopefully there'll be some new perspectives or something that will be interesting to you. And I'm doing it through the lens of the habitable zone. So diversity of climate states through the lens of the habitable zone. So first, thinking about planets like Earth, planets that have liquid water on their surface, thinking about hot planets like Venus, and thinking about cold planets like a Snowball. So I intentionally didn't put Mars there because it's just a planetesimal. So okay. So we're gonna have a little adventure today with three friends. First is the astronomer. So our astronomer friend, he's really good at plotting things on log-log axes, but he thinks that planets are just little dots. So we're going to see how he thinks about diversity of terrestrial planets. Then we're going to have our friend, the climate scientist. So she's really good at geophysical fluid dynamics, radiative transfer, computers, stuff like that. She can make really good models of Earth, how it is today, but her problem is that a long time for her is 100 years. And then we have the geologist. So the astronomer and the climate scientist kind of look down on him. He never passed calculus. He kind of looks like a hobo. But he's really good at observing stuff, and he can think on long time scales. And he's going to have a lot to contribute to. Okay, so first, I just want to talk, when we're talking about the habitable zone, NASA says follow the water. So we're thinking about liquid water on the surface of the planet. And obviously there could be other types of life that don't require liquid water and all this, there are more complicated things, but we're just going to use the traditional definition, liquid water on the surface of the planet. And what you can see here is a picture from Earth, which is a planet that has liquid water. And you can see that at the bottom. When you have liquid water, you get other forms of water too. So you get ice, solid ice there. It has the weird property that it floats on the surface of the liquid water, and it's much lighter, so it reflects light. So that can have a huge climate impact that we're going to talk about. You also have water vapor, which you can't see, but that has an important radiative effect, and that's going to come up today. And then you have solid and liquid phases of water suspended in the atmosphere, which we call clouds, and you can see those there. And they can have a really important radiative effect that some people have talked about in the conference today, but that we're not going to focus on in this talk. So we are going to focus on the liquid water, which you can see is dark, the floated solid water, which is ice, which is bright and reflects sunlight, and water vapor in the atmosphere, which absorbs infrared radiation and causes a greenhouse effect. Okay, so here's the astronomer doing the first calculation of the habitable zone. So the astronomer says, by the Stefan-Boltzmann law, the insolation is proportional to the temperature to the fourth power. And then just by basic geometry, the insolation is proportional to the distance between the star and the planet to the -2, so that the distance should be proportional to the temperature to the -2. And then he says, well, the temperature of Earth is 288 Kelvin, about. And so we're going to say the outer edge of the habitable zone is the freezing point of water, 273 Kelvin. And we're going to say the inner edge of the habitable zone is the boiling point of water on the surface of Earth, which is 373 Kelvin. And we're just going to scale by 1 astronomical unit, which is the distance between Earth and the sun. And we're going to say, so the inner edge by that scaling is 0.6 AU, and the outer edge is 1.11 AU. And this calculation assumes that the albedo and the greenhouse effect, the emissivity of the planet, of the atmosphere, stay constant, so that nothing changes as you change these distances. And if you do that, you get a habitable zone that looks like this. So I'm going to show a bunch of different pictures of what sort of a habitable zone you would get. And what this sort of means is an Earth-like planet, a terrestrial planet like Earth, is going to be in that range with liquid water at the surface. And the distances are to scale. So those circles around the sun have distances to scale, 0.6 AU and 1.1 AU. When I change those will be to scale. The planets that I put in them and the sun are not to scale. So this is what the astronomer thinks. He thinks that you have a fairly wide habitable zone and Earth is at the outer edge of it, near freezing over. Okay, so now the climate scientist comes and adds some things to the picture. So the climate scientist says, well, actually, there are some positive feedbacks in the climate system that you didn't take into account. And the first one is the water vapor feedback. And so as you can see on the left here, in the lower left, you see an ocean. So we're imagining a surface that has an ocean, a water reservoir, and there's surface radiation coming out of that reservoir, this red arrow. The size of the arrow is proportional to the intensity of the radiation, infrared radiation. And then there's an atmosphere with water vapor in it, and the atmosphere absorbs some of that radiation, and so the radiation that's being emitted to space is smaller. So that's all you can see on the left-hand side. And then if we imagine that this planet warms a little bit, the ocean gets warmer, so it's going to emit more radiation, but what happens is the atmosphere also gets warmer, and so there's more water vapor in the atmosphere by the Clausius-Clapeyron relationship. And so the emission to space, although the emission to space is larger than it was before, it's not as large as it would have been if the water vapor didn't increase. So we have a warmer surface, a warmer atmosphere, more water vapor that causes a stronger greenhouse effect and less emission to space. And that's going to warm the planet more. So it's a positive feedback. And that's something that was neglected by the astronomer. That's terrible. Sorry, I made this in Keynote, and I didn't get, when I checked, I only checked the first few. So anyways, what this is showing is, I'm just going to sort of talk about it, is a runaway greenhouse effect. So you can look at me, you don't have to look at that terrible slide. So the runaway greenhouse effect, the basic idea is if you had a planet with no atmosphere, it would just emit like sigma t to the fourth. So it would be really simple. But if you have an atmosphere with water vapor in it, the water vapor has this positive feedback. And eventually, as the optical thickness of water vapor starts to be greater than 1 by the surface of the planet, you have a limit on how much you can emit to space because the temperature profile starts to just be set by the water vapor pressure Clausius-Clapeyron relationship. And so there's a maximum amount that you can emit to space. And if you absorb more radiation than this, then then in the infrared, you can't emit all that radiation. You have to warm up until you're emitting in regions where water vapor can't absorb. And so this is the runaway greenhouse process. And it's the natural sort of, it's the end state of the positive feedback, water vapor feedback. And that marks the inner edge of the habitable zone to the climate scientist. And so that's where a planet like Earth turns into a planet like Venus. And we've had some talks on this already. We think this happened in Venus's past, at least some people do, and it's going to happen in Earth's future, the runaway greenhouse. And the climate scientist, she takes a global climate model, which is it's basically a big fancy model where you discretize the equations of motion for the ocean and for the atmosphere. So the equations of motion tell you about the fluid dynamics. And then you also solve the radiative transfer equations, and you couple those all together. And then any processes that are at too small a scale for the discretization that we have, the grid scale, which is about 100 kilometers by 100 kilometers, so things like clouds and convection, they get parameterized. So she puts them into the model, like if the temperatures on the grid scale is such and such, and if the moisture is such and such, then you make clouds like this. So that's how the climate model works. And when she puts all this stuff in and then solves for the runaway greenhouse, she finds that it's about 0.95 astronomical units. So it's just a little bit in from where Earth is. So that's a huge cutoff of habitable region from what the astronomer thought. So this water vapor positive feedback has a huge effect, is the bottom line. Second feedback that she points out is that on a planet with an ocean, there's an ice-albedo feedback that can be important, where you're replacing dark water with bright ice, and that reflects sunlight when you get colder. So this is a little diagram of that. You have an ocean and you have some ice floating on it. There's sunlight coming in and sunlight being reflected by this whole system, the ocean and the ice. And the arrows here represent relative magnitudes. And if you start to cool that system off, it gets colder with the blue arrow, the ice expands and all of a sudden you're reflecting more sunlight. And so as a result, you're getting colder and making it easier for the ice to expand. And we call that positive feedback the Ice-albedo feedback. That's our climate scientist's second feedback. And so that feedback, if it goes all the way, the asymptotic state is to go to a snowball planet. And when she puts this into her climate model, she finds that it occurs at 1.05 astronomical units. So it cut off a little bit of the astronomer's habitable zone. And what this means is that the climate scientist has a habitable zone that's super narrow. So if if Earth were just a little bit closer to the sun, it would be like Venus. And if it were just a little bit further from the sun, it would be like a snowball planet that may have happened in Earth history. And she doesn't think that CO2 can change. It just stays constant with time. And so there's no way, from her perspective, to get out of the snowball planet. And all of you who know about the faint young sun problem will be saying, what about early Earth? You know, if a planet like Earth can only turns into a snowball with just a little bit less sunlight, how can you explain the fact that early Earth wasn't in a snowball, even though the sunlight was much weaker, 30% weaker? Okay, and this is where the geologist comes in. So the geologist points out a really critical long-term feedback. So all those climate feedbacks were quick feedbacks. And this is a long-term feedback on 100,000 year to a million year time scale, the silicate-weathering feedback. And so this is a little diagram of the carbon cycle. So at the bottom you have the mantle in red, and then you have continent in orange, and that triangle is a volcano. And so CO2 is coming out of the volcano, and actually those volcanoes could be under the water, they could be on the land, whatever. It's just sort of a schematic. And CO2 is coming out, and then you have a cloud with rainwater, and the CO2 is dissolving in the rainwater, and then it's falling and hitting the rock surface, and it's leaching off calcium and magnesium ions, and they go into the ocean, and then they join up with carbonate ions, and they make calcium carbonate or whatever, and they fall into the ocean crust, and then eventually they're subducted into the mantle, and that closes the cycle. But the critical part of this system is the weathering that happens with this warm rainwater. And the reason that that's important is that if you warm the planet up, there's more rain, and also these weathering reactions may be temperature dependent, so they may run faster if the temperature is higher. So if you do something like increase the insolation, those reactions are going to, and try to warm the planet up, those reactions are going to run faster and pull CO2 out of the system. And so the CO2 is going to be smaller, and it's going to buffer the system. It's a negative feedback. So you won't get as much surface temperature increase as you thought you would. And if you decrease the insolation, like going back to the faint young sun, those reactions are going to run slower, and so you're going to have CO2 build up in the Earth atmosphere system. So this is the big negative feedback that the geologist delivers to us. Okay, and now I'm going to talk about a coupled climate carbon cycle model. So we're going to have an equation for climate, and we're going to have an equation for the carbon cycle, and I'm going to represent those equations using these scales. So if the equations are balanced, then you have an equal amount of weight on either side. And the terms in these equations are carbon dioxide in green, so you can see the terms at the bottom. Temperature in orangish color. Is that red or orange? Red. Temperature in red, thank you. Insolation is in yellow, and the brown, which is coming out of the Earth, is outgassing. And so for climate, the things that warm the climate are higher CO2 and more insolation. Those are positive terms on the climate. Temperature is actually a cooling term on the climate, because if you increase the temperature, you emit more radiation to space. And so we can have a balance from insulation and CO2 balancing temperature cooling. And the planet that we're thinking about on the left column here, I haven't plotted the other planet yet, is a high insulation. So we have a large square, a large weight for insulation. For the carbon cycle, we have an outgassing term, which is that brown on the left, and that's being balanced by the CO2 weathering, which is dependent on both the CO2 and the temperature. So this is a setup we have with everything balanced for a high insulation planet. And if we go to a low insulation planet, what happens is that insulation square in the climate balance gets smaller, and the CO2 square gets bigger, so that the temperature, even though the insulation is a lot lower, the temperature is only slightly smaller. It's only slightly less. And if we look at the carbon cycle, the outgassing stayed the same, but now the balance, in the weathering balance, the CO2 is relatively more important because the temperature got smaller. And the temperature can only get a little bit smaller even though the CO2 gets a lot bigger, because there's a much stronger dependence on temperature. In most of these models, you assume an exponential dependence on temperature of the weathering rate. Okay, so this is sort of how this negative feedback, the silicate weathering feedback, can work if we think about large changes in insulation. We end up getting large changes in CO2 to balance them. And as a result, we get a wide habitable zone again. And so now what we see is the inner edge of the habitable zone stays roughly the same, because there's not really any action left. The CO2 for a planet like Earth is already really small, so you don't really get much bang for removing the CO2. You still get the runaway greenhouse in about the same place. But the outer edge goes from 1.05 astronomical units all the way to 1.7 astronomical units, because as you move the planet outwards, you get more and more CO2, and you can stay warm. Okay. Now I want to talk about something that I learned about at the last CCTP meeting from a talk by Jim Casting, and I thought it was really cool, and I wanted to work on it. And so this is the whole picture that the geologist just showed us depends on there being enough CO2 outgassing to balance the weathering. But what happens if you're in the modern climate-like state and your weathering terms are just too big to balance that outgassing term, and you just keep drawing down your CO2? What happens to a planet like that if your carbon cycle is out of balance? And to do that, we need to know something about climate hysteresis. So this is a diagram from a simple climate model. And on the vertical axis, you have the ice latitude. So that's the latitude the ice goes to. If it's 90 degrees, that means there's no ice on the planet. And if it's 0 degrees, you're in a snowball. And so I have these little diagrams here. This is something like modern Earth is up high at ice latitude, and something like a snowball Earth is at low ice latitude. And this picture, and then the horizontal axis is the radiative forcing. So that's something like the logarithm of the CO2. So this is a simple model that you don't put in the CO2, you put in something called radiative forcing. But think of it as the log of the CO2. And this line here is the solution to the model. And the solid parts are stable states that attract the model to it. Those are stable states. And then this dotted line is an unstable state, which is a separation barrier between the two stable states. So if you started a state here, you'd end up here, and if you started it here, you'd end up down here. And then at these intersections, you have what's called a bifurcation, where a stable state ceases to exist. And then you'll notice that for a large range of radiative forcing, the system's bistable. So you can either be in an icy state where you're reflecting a lot of sunlight, and so it stays cold, so the ice is happy, or you can be in an ice-free state where you're absorbing a lot of sunlight so that it stays warm, so that the water is happy. Okay, that much of this is contributed by the climate scientist. And then the geologist tells us that if we start in an ice-free state and the CO2 starts to be drawn down for some reason, eventually we're going to hit this bifurcation and we're going to go into the globally ice-covered state. But then the weathering is going to be very, very small in the globally ice-covered state. So we'll build up CO2 from outgassing over millions of years, and then we'll hit this other bifurcation and we'll jump into the warm state. So this is a combo of the geologist and the climate scientist. And it tells us that we can have what's called hysteresis. We can have state dependence as we vary the CO2. And that's important for what we're going to talk about right now. Okay, so climate limit cycles, they're the result. So what we have here, we're going to look at two time series. And notice the scale on the x-axis is millions of years. They're time series of the carbon dioxide, and that scale is bars. Okay, so like as much carbon dioxide as is in the total pressure of Earth's atmosphere. And then we have temperature, where we're going from like minus 40 Celsius to 0 is freezing to 40. And this is a schematic diagram. So this is not quantitative. These are sort of rough values. And so we've assumed that in the warm state up here, our weathering equation is out of balance with more weathering than outgassing. And so that's what we're showing with these first lines. However, our climate state right here, our climate equation is still in quasi-balance. And so in this slightly out of balance system, we're slowly drawing down the CO2 until we hit the snowball. When we hit the snowball, so notice look at the climate scale. When we hit the snowball, the albedo increases, and that reflects more sunlight. And so our insulation, our absorbed insulation square shrinks, and all of a sudden the climate is out of balance. And really quickly, we jump down in temperature to a very low temperature. But now, since we're at a low temperature, the weathering gets really small. And all of a sudden, our weathering equation is out of balance in the other direction. We have CO2 building up because there's more outgassing than our teeny weathering because the CO2 and the temperature are so small. But during this phase, the climate equation is back in quasi-equilibrium. So the temperature is slowly changing, but at every CO2, the climate is in quasi-equilibrium. And we do that until we hit the other bifurcation, and we jump out of the snowball state. And this time, we replace ice by liquid water, and we get an out of balance equation where we're super warming the planet. And then we get these cycles like that. And so if we're talking about a planet habitability in the traditional sense, where we have sustained long-term liquid water at the surface, this doesn't meet the definition. And so all of these guys get together, and we've got the astronomer, the climate scientist, and the geologist, and they say, well, this outer edge may actually be variable, and it may depend on the planetary outgassing, so an internal property of the planet. And if the planetary outgassing is high enough, maybe you get that whole habitable zone that the geologist told us we can have. But if it's a planet with a low CO2 outgassing, then maybe we cut off the outer region and we get limit cycles in there instead of getting a sustained warm climate. Okay, so I'm just going to review, and then I hope, is there time? Yeah, so I was trying to leave some time for questions and discussion, so I think that worked. So the astronomer just did a sort of scaling analysis, assuming that the planet is a dot where things don't change. And he told us that there's a fairly wide habitable zone, and Earth is towards the outer edge of it. The climate scientists included two positive feedbacks that we see on modern Earth, the water vapor feedback and the ice-albedo feedback. And as a result, the region where you can have a planet like Earth got drastically shrunk. And then the geologist came and told us that actually there's this long-term negative feedback on 100,000 or a million-year time scale, the silicate-weathering feedback, that can buffer the CO2 so that the temperature doesn't change very much on a planet. And you can get a much wider habitable zone extending way back in time for Earth and way out in space for the modern solar system. And then when all of these guys got together, they also noticed that you can have limit cycles if your CO2 outgassing is too small. And so this is sort of a reminder that everyone should collaborate and think broadly. And I think that's good for this meeting, because that's what we're trying to do. And one last thing is we forgot to invite one friend to the party, and that's the biologist. And so we need to think about what the biology on a planet like Earth can do to these cycles. And that's where I'm going to end. So thank you.
So we have time for questions.
Hi, great talk. So as an exoplanet astronomer, when we go and grab lots of Kepler and test exoplanets, should we talk about maybe the not habitable zone, or how would you suggest characterizing our planets by one simple number, even if it's very reductive, given these different constraints?
So can you be more specific?
Sure. Let's say that we have 10,000 planets,
Yeah.
and out of those 10,000 planets, let's say that some number of them are in the traditionally defined astronomer habitable zone.
Yeah.
And some other number of them are within the geological habitable zone,
Oh, yeah.
or the climate habitable zone, or so forth. So would you like to see, as an astronomer, us
Yeah.
provide tables of, which planet falls into which category, or how we talk about planets being in the traditional habitable zone or not, or kind of what would your thoughts be on what you'd like to see coming from the
so if you're
exoplanet
looking
discovery machine?
Yeah, so if you're looking for habitable planets, I think you want to use basically one of these ones. So the ones that include the silicate-weathering feedback. I mean, if we're assuming that thing works, that's what most people are assuming, then that's roughly what you want to be looking for. So the astronomer habitable zone, I was just putting that up kind of as a counterpoint. I don't think you should use that one to look for planetary habitability. And if this is the real one, if there's no silicate weathering feedback, then we're going to be have a lot of trouble finding habitable planets. Let's just say, because there'll be if this is the real habitable zone, it would mean that the reason that Earth is habitable, has stayed habitable for 4 billion years, is a total accident. For some random reason, as the insulation has changed, the CO2 has just randomly adjusted to exactly counterbalance the insulation increase, and there's no reason behind that. And we're just here because that happened, which is a possibility, okay? But if that's true, then habitable planets like Earth that can stay habitable for billions of years are going to be super rare. But I find the geological evidence for this silicate weathering feedback strong. And you can see that in things like, you can see evidence for that in the glacial cycles, how the CO2 is always returning. In the last few million years when we've had glacial cycles, the CO2 is always returning to roughly the same value. And you can also see evidence in that from things like, there's something called the Paleocene-Eocene thermal maximum, where there was a huge increase in temperature and a perturbation of the carbon cycle that we think represents a big slug of carbon dioxide, and then the temperature decays on exactly the right time scale, about 100,000 years, that we would expect the CO2 to be weathered out. So there are evidences that seem to suggest this thing is working. So I would go with this habitable zone, something like in the Koperapu papers, potentially modified by newer 3D calculations, including clouds.
Okay, so So I agree that there's plenty of evidence that silicate weathering has operated on Earth, but there's also, my understanding is that it's still fashionable to think that some of the dominant greenhouse gas way back when might have been methane or something else on Earth.
Yeah.
In which case, it does sound like maybe it's a mixture of like a stabilizing feedback and then some fluke involving life that we made habitable.
Yeah. So if you believe this stabilizing feedback, so the question there, so some people think that the CO2 wasn't high enough on early Earth to explain the temperatures based on CO2 proxies. Those are really uncertain, and we shouldn't put too much weight on them. But even if that's true, and you need it on Earth, methane or hydrogen or something else, which is possible, then this thing is like a capacitor. It would provide, if you happen to have had less methane, then you would have just had more CO2. So on a planet that happened to have more methane, you would have more CO2 and you'd be okay. The exception is if you're outside the traditional habitable zone and there's a ton of hydrogen at a point where CO2 would be condensing out, which is what marks this outer edge of the habitable zone. In those cases, then it would be different, and so you could be habitable because of extra hydrogen. But for a planet like early Earth, if there had been less methane, there would have just been more CO2, if you believe this story.